All right, so this lesson is going to be a review of all of Chapter P, Section 2. All right, so this is in preparation for your upcoming test. All right, so we're going to get started just with a couple major topics that we've seen so far. All right, so starting with adding exponents. When you see an expression like this where, okay, you have x to the third power and another x to the third power, here you can combine like terms, right? You see an addition in between them, so we're going to combine like terms. All right, now this first term, right, x to the third power, we don't see a coefficient in front of it, so we assume it's 1, right? So if you're ever unsure, just write the 1 in front, right? It's better to be safe, right? And so now that you can see it, you may remember to add the 1 and the 2, right? But I saw a couple mistakes like this on the quiz, right? So if it's helpful for you, write the coefficient, right? So here we're just doing 1 plus 2, right? And so we get 3. And then x to the third power is our variable, so we're going to leave that alone, right? So we're going to get x to the third power. 3x to the third power is our answer for this one. And now this next example with the radicals, right? 2 radical 3 plus 3 radical 2. Right, so I mentioned in class, we always want to treat the radicals like a variable, right? Here, our radicals are not the same, right? Notice I have a radical 3 and a radical 2. The numbers under the radical are not the same, so we cannot combine these, right? So we're just going to leave this alone. This is just going to be 2 radical 3 plus 3 radical 2, right? We leave it the exact same. And now if this is confusing for you, think of it like variables, right? Can you add 2y plus 3x, for example? You can, because the variables are different, right? Same way with square roots, right? If I have a different square root, then you can't add them, you just leave it alone. All right, now on that note, if you have the same radical, so 2 radical 3 and 3 radical 3, right? I have the exact same number under the radical. Here you can add them like normal, right? As if we're combining like terms with variables. So I'm just going to add the whole number plus the whole number. 2 plus 3 is going to give you 5. And the number under our radical is radical 3, right? So our answer is going to be 5 radical 3. And again, if this is confusing for you, think of it like variables. What if it was 2x plus 3x, right? They're like terms. They have the exact same variable, so we can combine it to be 5x. Same way with radicals, right? I have a radical 3 and a radical 3. You can combine the whole numbers out front. All right, good. Now, multiplying with exponents. Our rule for multiplying with exponents is that if we have the same base, right? So in this example, our base is x. We do have the same base. When we have the same base, we add the exponents, right? So our exponent on the first one is 3, and on the second one is going to be 2. So we get x to the 3 plus 2, right? This is going to give you x to the power of 5. All right, and now what if we have coefficients in front, all right? Nothing to worry about there, right? Since we're multiplying, we're just going to multiply coefficient with the coefficient, x with the x, right? So 3 times 2, we're going to multiply those and we're going to get 6. And then x to the power of 3, x to the power of 4. Again, when you're multiplying by the same base, you add the exponents. So x to the 3 plus 4 is going to give you x to the 7th. All right, good. And now on that note, we're going to go into dividing with exponents. Now, I always like to make this comparison. If when you multiply with exponents, you add them, what do you think we do with dividing exponents? Right? When we're dividing with exponents, we're going to subtract the exponents, right? So they kind of go hand in hand. Right? So this x to the power of 7 over x to the power of 3. I know it's a little hard to see, but that's, right, that's a 7 and that's a 3. Right? We're dividing and we have the same variables, right? We're going to subtract, right? So x to the 7 minus 3 is going to give you x to the power of 4. All right, good. It's always the top exponent minus the bottom exponent. All right, and now the next example, right? We see the same exponents except they're in a different order. Now we have x to the third power on top, right? Same as before, we're going to do the top exponent minus the bottom exponent. This is going to be x to the third power, x to the third power minus 7. Right? And then 3 minus 7, we're going to do x to the negative 4. Right? Can we leave this alone? No, we can't, right? So anytime you see a negative exponent, you want to simplify it by moving this to the denominator. Right? So this is going to become 1 over x to the positive 4. Right? Anytime you see a negative exponent, your answer is not simplified. Right? So be sure that your final answer on the test, you don't see any negative exponents. You need to simplify it. All right, good. All right, and now this next example, right? We're still dividing with exponents, just this time we have coefficients out front. Right? So our coefficients are 5 and 15. Now, a common mistake I saw on the quiz was a lot of people, right, are still thinking in the world of exponents, and you might think to subtract 5 minus 15 to get negative 10. Right? No need to overcomplicate it, right? We know how to simplify fractions, right? Coefficients we just treat like whole numbers, which they are, right? So 5 and 15 we're going to divide by a common factor. Right? So 5 we can cancel, and 15 we can cancel. 5 is going to turn into a 1, divide 5 by 5, and divide 15 by 5, you get 3. All right, let me write in a darker color. That doesn't look that dark. Right? So 1 over 3. All right, so I'm just going to go ahead and rewrite this. Oh, looks like my Apple Pencil is glitching a bit. All right, so let me just rewrite this. 1 over 3, right? That 5 became a 1, that 15 became a 3. And then x to the third power over x. Anytime you don't see an exponent on your variable, you always want to write a 1 so that you know that you have to subtract a 1 from it. Right? So this becomes x to the 3 minus 1. Right? And then 3 minus 1, we just get 2. Right? So we get 1x squared over 3. Right? Now, if in your final answer you get a coefficient of 1, you don't have to write it, right? So this is the same as saying x squared over 3. Right? It's the exact same thing. Now, you're not going to get points off if you leave the 1 out front, right? It's just a little bit redundant. You don't need to write it. All right, so this should be your final answer. All right, so we're going to continue on the topic with exponents. Now, before I continue, I just want to make a remark. Right, I encourage you, try these examples on your own, especially if you weren't present in class or maybe you just didn't get all the notes out. Try it on your own and then compare your answers with mine. See where you went wrong, right? The best way to practice is to try them yourself, right? So I encourage you at any moment, if I'm going over a problem, pause the video, see if you can do it yourself, and then check your answer. All right, that's my suggestion. All right, and now moving along. Okay. Now, when you raise a power to a power, you always want to multiply the powers, right? You hear me say it all the time in class, right? Power to a power, you multiply the powers, right? In this first example, I have x to the third power to the 7th power, right? Power to a power. Whoa, hold on. All right, power to a power, you want to multiply, right? So this becomes x to the 3 times 7. Oh, again, looks like my pencil's glitching a bit. All right, so this becomes x to the 21st. All right, simple as that. All right, and now when you have an exponent over multiple factors like this one, right, this exponent is going to go to each factor in the exponents, right? So this is going to become 2 to the third power, right? So 2 to the third power, and then times x to the third power, right? And then 2 to the third power, we know that that's 8, right? 2 times 2 is going to get you 8. And then x to the third power, Again, power to a power, you want to multiply the powers. X to the 3 times 3 is going to get you x to the 9th. All right. And now the next example is just one extra component to it, right? So in each of these examples, we're adding something a little bit extra, right? So now in this one, not only do we have factors, but we also have things that are being divided. When you see something like this, right, the exponent is going to go to each factor on the top and on the bottom, right? So we're going to write this as 2 to the third power, right, times x to the third power over y to the third power to the third power. And then 2 to the third power, we had said that that was 8. And then x to the third power, we leave that alone. And then y to the third power. Again, power to a power, you're going to multiply the powers. This is going to become y to the 9th. All right, so this should be your final answer. All right, good. And now negative exponents, right? All a negative exponent does is just switch its place, right? In class, a lot of you are going to say flip it, right? So you're going to flip it, right? So, for example, 2x to the negative second power, right? The negative 2 over the x, this just means that we're going to move this to the denominator, right? And then we see a negative 3 on the y. This just means we're going to move it to the numerator, all right? And then we leave 2 alone, right? 2 is our coefficient, and there's no exponent over it, right? The negative 2 is only going to the x, not the 2x, right? So we leave the 2 alone. All right, so we're going to get 2, and then y to the negative 3 turns positive by bringing it to the numerator. So 2y to the third power over, and then x to the positive second power, right? We turn that one positive by bringing it to the denominator, right? So again, all the negative exponent does is just switch its place, right? If it's in the top, it's going to move to the bottom. If it's in the bottom, it's going to move to the top. All right, and that's all you need to do for that one, right? There's nothing you can do to further simplify it. All right, good. And now, this next one, right, we see a negative exponent over a fraction, right? Now, my personal favorite way to do these, right, is to get rid of this negative exponent right away by flipping the top and the bottom, right? So, again, to simplify this negative exponent on the outside, all I'm going to do is I'm going to switch the place of the top and the bottom right away. Y to the third is on the bottom, it's going to move to the top. So we get y to the third of top. 2x to the negative 3 is on the top, so I'm going to move it to the bottom. All right, and it's all to the second power. Now, a common question I got in class is why don't we move, or why didn't the x to the negative 3 become positive? Right? It didn't become positive because we didn't move it to the bottom because of that negative 3. We moved it to the bottom because of this negative 2. Right? So moving x to the negative 3 didn't make the negative 3 positive. It made this 2 positive. Right? So this one right here. Right? And now, to simplify the x to the negative 3, we move this negative exponent up top. Right? So then we get x to the third power times y to the third power over 2, right? 2 is left alone on the bottom, and this is all to the second power. Another common question that I got was, is your answer still correct if you write y to the third power first? So if you had y to the third times x to the third over 2. Yeah, it is correct, right? Multiplication is commutative. I just like writing the x first because alphabetically it just comes first, right? That's pretty standard. All right. And then now the last thing we do, right? This looks like a previous example. All you have to do is raise everything inside the parentheses to the second power. All right, so we get x to the third to the second power, y to the third to the second power, over 2 to the second power. All right, and then again, power to a power, you multiply the powers. Same thing with this one. Then we get x to the 6th, y to the 6th, over, and then 2 times 2 is 4. All right, good. So it was a little bit more involved, right? It required a lot more steps. right? Now you could have taken a couple different approaches to solve this problem, right? But I find that the more negative exponents you give yourself, the more easy it is to make mistakes, right? So a lot of kids might take this -2 and put it to each factor right away, right? That's perfectly valid, but you have more negative exponents. So down the line, when you're doing your work, you might forget to flip it and you're going to leave it on the top when it should have been on the bottom, right? Or you might have a sign mistake. Maybe when you do 3 times -2, you write +6 instead of -6, right? So just a lot of room for error, right? So that's my preferred method, right, is to flip it right away. Get rid of any negative exponents right away. All right, good. Now moving along to fractional exponents, right? So with these fractional exponents, your denominator is going to be your index, right? So x to the 3/2. For example, this 2 on the denominator is going to go out front to be your index, right? So this is going to become the square root of x. And then you have a numerator of 3. The numerator is going to stay as the exponent, right? So in exponential form, this is going to become x, or square root of x to the 3rd power. All right. And same story when you see a number, right? So when your base is a number. Now, when your base is a number, you want to actually evaluate it, right? You never just want to leave it in radical form. Chances are it's going to simplify to be a whole number. All right, so let's see if this works. Let's see if that's the case here. All right, so I have 2 in the denominator. Again, this is going to go out front to be your index of the radical. All right, so I get the square root of 16, and then to the 3rd power. All right, our numerator is 3, so it's going to become to the 3rd power. And then you don't just want to stop here, right? If you stop here, you won't get full credit, right? You need to actually evaluate this, right? We know what the square root of 16 is. We know that this is going to give you 4. Right? And then we have to raise it to the 3rd power, right? So 4 to the 3rd power, we just do 4 times 4 times 4 is going to get you 64. All right, and now the next example. All right, this is another one that I see a lot of mistakes on, right? So this negative in the exponent, right? This is where, this is where I see the mistakes. Some people make their entire answer negative, right? It doesn't make your entire answer negative. It just switches its place from the numerator to the denominator. And another common mistake I see is they flip this fraction in the exponent, right? You never want to flip the fraction of the exponent. If your exponent is a fraction, leave it alone. The only thing that this negative exponent is flipping is the base. Your base is 16, right? Your base is not 3/2. 3/2 is your exponent, so you leave that fraction alone, all right? So first thing we want to do, take care of the negative exponent, right? All that's going to do is going to bring it to the bottom, right? So we're going to get 1 over 16 to the positive 3/2. And now from here we can write it in radical form and simplify, right? And we actually did this in the previous example, right? Square root of 16 to the 3rd power. Square root of 16 is 4 to the 3rd power. Is going to give you 1 over 64, right? We evaluated it right here. All right, good. All right, and now getting into just some special cases, right? This is all fair game that you might see on your exam. All right, first, anything to the 0 power is 1, right? So I see this 0 in the exponent over this set of parentheses. That means this entire thing under the parentheses is going to go away. This entire thing is going to become 1. All right, simple as that. All right, this is another one that I see a lot of kids overcomplicate, right? Nothing complicated here. Anything to the 0 power is 1, right? Whole number 1. All right, and now the next example. Anytime you see a 1/2 in your exponent, this just means your square root, right? So you could even do the whole process of writing it to the index, right? 1/2 in your exponent just means square root. Right? So square root of 25, we just get 5. All right, and now the next two examples, all right, so actually the last 4 examples on this page are ones that I see a lot of common mistakes on, right? So as you can see, they're not overly complicated expressions, right? They're actually fairly short, right? But there's a lot of conceptual errors that you might make on the test, right? So just be mindful of that, right? This first one, -5 to the second power. Well, the difference between this expression and this expression is the set of parentheses, right? This first expression, -5 to the second power, this just means our final answer is going to be negative, right? This negative out front. You can think of it like a -1 times 5 to the second power. And now we know 5 to the second power is 25, so we do -25 as your answer. And now this next example, this square is going to all of -5, right? So this means -5 times -5. Right, -5 times -5 is going to get you positive 25. All right, nice, good. And now, the next two examples, again, I see a lot of common mistakes on these, right? This first one, -25 to the 1/2, right? We don't see the negative in parentheses, so we're not going to raise the negative to the 1/2. We're just raising 25 to the 1/2. Right? And then our final answer is going to be negative. Again, you can think of it like a -1. Right? So this becomes -1 times, and then 1/2. As your exponent, we said that that means the square root. Right? So we take the square root of 25. So we get -1 times 5. So -5 is your answer. And now this next example, right? 1/2 is in your exponent of the entire thing. Right, so this becomes the square root of -25. All right, now this is going to be no real solution. Right, because, all right, if you think about it, what can we multiply, or what number can we multiply by itself to get -25? Well, if you try 5 times 5, that's going to get you positive 25. Now, if you do -5 times -5, again, that's going to get you positive 25. So what can we multiply to get -25? Right? Nothing. Right? This is going to give you no real solution, and this is always going to be the case when your index is even. Right? Now, this is an example that I've gone over in class when I first taught the lesson. Right, and so a lot of people remember it, and anytime they see a negative under a radical, they'll say no solution. Well, that's not always the case, right? Because let's take, for example, the cube root of -125. So you might see the negative under the radical, and you're going to say, okay, well, it's no solution. Okay, well, what's different about this one? Our index is 3, right? We have an odd index, right? This is actually going to become -5, right? Because try it, right? -5 times -5 gets you positive 25. And then when you multiply by -5 again, it turns back into a negative, -125, right? So it works out with odd indexes, or indices, I'm sorry. But it doesn't work out when the index is even, right? Like in this example with the square root. All right, good. All right, one more slide for this review, and this is all on section P2D or P2C, depending on what it says, but it's the section on simplifying square roots. All right, so let's start with this first example, right? It's just asking you to simplify square root of 200, right? So now an answer or an expression like this is fully simplified when you can take the square root of all of the factors that are perfect squares, right? So here, we're going to break 200 up into factors that are perfect squares. Now, you might think of a variety of different things, right? You might think, or in class, I heard 8 and 25, 20 and 10, right? All those, like, any factors that you can think of that multiply to 200 are perfectly valid. But the best one to use is going to be square root of 100 times the square root of 2, right? 100 times 2 gets you 200. And this is the best pair of factors to use because you already eliminate your biggest perfect square, right? 100 is a perfect square. This becomes 10. And then you just multiply your answer by the square root of 2 and you get your answer right away, right? So hopefully you see why this is the best option when you're choosing your factors. Now you could have done any number of factors. All right, so let's say you did 20 and 10. All right, 20 and 10. All right, let's say you do the factor tree and you want to break them down. All right, and then 20, hopefully you can see right away that you can break it up into 2 and 10, and you already have a pair, right? Anytime you have a pair of radicals, it shows up once outside the radical. All right, so this becomes whole number 10 times the square root of 2, right? Square root of 2 is the little leftover, right? You could even try it with another pair of factors, right? So maybe you did 8 and 25. All right, square root of 8, square root of 25. Now, hopefully here you can see that square root of 25 is going to get you 5, all right? And now all you have to do is simplify square root of 8, right? This just becomes square root of 4 and square root of 2. And then square root of 4, again, is a perfect square. We get 2. Now we can multiply our whole numbers, 2 times 5, to get 10. And then again, square root of 2 is a little remainder. Right? It's a little leftover. No matter which way you do it, you'll get the same answer. But try to find the biggest perfect square that you can, right? Because as you can see, this one took one step to solve, right? Whereas if you have a whole factor tree, right, this is another one that I see a lot of mistakes on because you might have a lot of different little trees on your paper and then you're circling pairs, right? And then you lose count of how many pairs that you circle, right? So there's a whole lot of room for error, right? So try to recognize the largest perfect square in your factors right away. All right, good. And now adding and subtracting square roots. All right, so like I mentioned in the first example, right, we want to treat the square roots, or we want to treat the radicals like a variable, right? So in this first example, 2 radical 3 plus 5 radical 3. Okay, well, they both have a radical 3, right? When this happens, we can add the whole numbers, right? 2 and 5. 2 plus 5 gets you 7, and you have 3 under a square root, so it's going to become 7 square root of 3. Right, nothing to do under the radical, right? You treat the radical like a variable. Again, you can think of it like 2x plus 5x, right? This is just going to give you 7x. You don't do anything to the x's. All right, and now the next example, right, we're going to do the same thing but with subtracting. Right, square root of 3, square root of 3, right? They're like terms, so to speak. All right, so we can just subtract the whole numbers. 2 minus 5 is going to get you negative 3. And then our radical is square root of 3, so I'm going to leave that alone. And now the next example, right, we see 2 square root of 2 plus 5 square root of 3. Okay, well, there's a problem here. Now I have a square root of 2 and a square root of 3. They're different. Right? When they're different, you leave it alone. You can't do anything to this, right? 2 square root of 2 plus 5 square root of 3, right? 2 and 3 cannot simplify under a radical. They don't have factors that are perfect squares, right? So this is fully simplified, right? You don't want to do anything else to it. Again, if this is confusing for you, think of the radicals like a variable. Can you add 2x plus 5y? No, you can't, right? Because x and y are different variables. Just like square root of 2 and square root of 3, they are different radicals, right? So you cannot combine them. All right, and now when you're multiplying radicals, right? Multiplying radicals, you can multiply under the radical, right? So assuming the radical is the same, meaning they have the same index, then you can multiply underneath, right? So we see a radical 10 and a radical 15. All right, they're both square roots, so we can do 10 times 15 under the radical, so 150. And now this we want to simplify, right? Again, by breaking it up into factors of a perfect square and a non-perfect square. All right, now again, you can think of a number of different pairs of factors for 150, but the best one, right, is going to be 25 and 6. All right, 25 is your biggest factor that's a perfect square, right? This is going to become 5, and then square root of 6 can't be simplified any further, so we leave it alone. This is your answer. All right, we have a similar idea in the next example. So 2 square root of 3 times 3 square root of 5. Well, when we're multiplying, we want to do the whole number times the whole number, radical times a radical, right? 2 times 3 gets you 6, right? Square root of 3 times square root of 5. Again, we want to multiply under the radical. 3 times 5 is 15, right? And 15 doesn't have any factors that are perfect squares, so we leave it alone. Our answer is 6 radical 15. All right. These next two examples, there's a lot of room for error as well, right? This part kind of confuses kids a little bit, right? So, all right, let's go a little bit slowly, right? So 2 square root of 3 times 5, right? So I see this 2 square root of 3 on the outside of parentheses. This just means we're going to distribute. We're going to distribute normally, right? So this is going to go to the 5 and the 5 square root of 5. Right, so distributing, again, we do whole number times the whole number. 2 and 5 are both whole numbers, so we get 10. And then we do a radical times a radical. Now there's no radical on this 5 that we can multiply the 3 with. All right, so we're going to leave it as radical 3. And this 2 square root of 3 times 5 square root of 5, again, we're going to do the whole number times the whole number. So 2 times 5 is 10, positive 10, so I'm going to write plus. And then again, I'm going to do a radical times a radical. This time we do have a radical. So 3 times 5 is 15. They're both under a radical, so I'm going to write radical 15. All right, and this would be your answer. All right. And the next one's also a little bit challenging. All right, so I have 2 sets of parentheses. In each of them, we have things that kind of look like binomials. All right, so we have a binomial times a binomial. Right, we're going to FOIL. Right, so we do the first times the first. So 2 square root of 3 times 4. Right, again, whole number times the whole number. 2 times 4 gets you 8. And then there's no radical to multiply the radical 3 with, so we leave it alone. All right, and now we do the outer times the outer. Right, so 2 square root of 3 times 2 square root of 7. Again, whole number times the whole number. So 2 times 2 gets you plus 4. And then radical times the radical. 3 times 7 is square root of 21. All right, and now the inner times the inner is going to be 3 times 4 is going to get you plus 12. All right, there are no radicals, so I'm going to leave it as plus 12. And then the last times the last, right? 3 times 2 square root of 7 is going to be plus 6, right? Whole number times the whole number, 3 times 2, and there's no radical to multiply the radical 7 with, so we leave it alone. And now this is your final answer, right? It looks kind of crazy, right? We have 4 terms here, but all of these radicals cannot be simplified into factors of perfect squares, right? And none of the radicals are the same, right? 3, 21, and 7. None of the radicals are the same, so we can't combine them. Right, so there's nothing more that we can do to this. We just leave it alone. All right, this is our final answer. All right, and so 3 more examples. Right, so dividing radicals, here we have to rationalize the denominator. Right, so this first example, square root of 15 over the square root of 5. Right, so to rationalize the denominator, you're going to multiply the top and the bottom by the denominator. Right, so our denominator here is radical 5. So I'm going to do square root of 5 on the top and the bottom, they're going to multiply. On the top, 15 times 5 is 75. Take the square root over, and then square root of 5 times the square root of 5 gets you whole number 5. All right, 5 with no radical. And then we want to simplify 75, right? Square root of 75, right? So think to yourself, what 2 factors can you multiply to get 75, where one of the factors is a perfect square? Right, and here we get square root of 25 times the square root of 3, right, over 5. And then square root of 25, this is going to give you 5, and then times the square root of 3 over 5. And now the last thing you want to do is cancel out the 5 on the top and the bottom, and then you're left with just square root of 3. Now, there was an easier way to do this, right, in my opinion. You could have also recognized that when you divide radicals, you can divide underneath the radical, right? Same way with when you multiply radicals, right? So let's look up here. We were able to do 10 times 15 and write it under a radical. We can do the same thing with dividing radicals, right? So we see a 15 and a 5 under a radical. We can do 15 divided by 5 and leave it under the radical, right? So this also is going to give you 15 divided by 5 is just the square root of 3. Right, so divide by a common factor, right? 15 gets you 3, and then 5 gets you 1. Right, so over the square root of 1, but anything over the square root of 1 is just 1, and anything over 1 is itself. Right, so a lot less steps, right? But I just wanted to show you how to rationalize this denominator. All right, and now this next example, same numbers just flipped, right? So now that we know we can simplify radicals in this way by dividing, right, I'm going to try that here. Let's make it a little bit shorter. All right, so 5 we can get rid of to make 1, and then 15 we can get rid of to make 3. All right, so we get the square root of 1 over the square root of 3. And the square root of 1 is just 1, so we get 1 over the square root of 3. All right, so you might get to this point and are tempted to stop, right, because it seems like you've done something, right? But we want to rationalize the denominator. We still have a radical in the denominator, right? So again, square root of 3 times the square root of 3, right? And on top is going to be 1 times the square root of 3. So we get square root of 3 over 3, right? Square root of 3 and square root of 3 make whole number 3, right? And then this would be your answer. All right, and so this last example is very important, right? So not always are you going to get just a single radical in the denominator. You might see a radical with a whole number, right? So 2 plus square root of 3, right? To rationalize this denominator, you want to multiply the top and the bottom by the conjugate of the denominator. Now, if you remember what a conjugate is, right, it's going to be the exact same expression, right? But instead of a plus, we're going to have a minus, right? So we're going to do 2 minus the square root of 3 on the top and the bottom, right? And so on the top, we want a FOIL, right? First times first is going to be 1 times 2, which is 2. 1 times negative square root of 3 is going to be minus square root of 3. Square root of 2 times 2 is going to get you plus 2 square root of 2. And then square root of 2 times negative square root of 3 is going to get you negative square root of 6. Again, radical times a radical, you can multiply underneath, right? 2 times 3 is 6. And you leave it under the radical. Right? And then over. Now you could FOIL it out and cancel the two middle terms, but if you know the middle term is going to cancel every time, then you can just square the first, right? 2 times 2 is, 2 times 2 is 4. And then square the last, right? So square root of 3 and square root of 3 is going to get you 3, right? And a positive times a negative is a negative, right? So 4 minus 3. On the bottom, we're left with 4 minus 3. Right? And 4 minus 3 gets you 1, so anything over 1 is itself. And on the numerator, all of these radicals are fully simplified, and none of them match up, so your answer, again, just like a previous problem, we're going to have a bunch of terms that we cannot combine. Right, looks terrible, but it is what it is. Right, this is going to be your final answer. Right, no more radicals in the denominator, right? We do not like radicals in the denominator. If in your final answer you have a radical in the denominator, see what you can do to get it out, right? Because we don't consider that fully simplified. All right. I know that concludes the review, right? So this covers every major topic that you're going to see on the test, right? Again, practice these problems. All homework solutions are posted. Check your work and try it on your own, right? You're only going to get better if you practice these by hand on your own. All right. Good luck.